Hello class, in this video you'll learn how to draw a galvanic cell. To draw a galvanic cell, we will need to ensure our illustration is labeled and contains all of the key design features. Questions that you will encounter may either give you the half equations or the overall redox equation, and from this given information, you will need to identify and label the anode and cathode as well as the polarity of these respective electrodes. We will also need to show the direction where electrons are flowing using an arrowhead. We will also need to specify and label the electrolytes that's found in each half cell. We also need to clearly show where the site of oxidation and reduction is and write the appropriate half equations for each half cell. We also need to show the direction where the anions and cations are moving towards in the salt bridge. And lastly, we also need to include an electrical device connected along the circuit to tell us whether the redox reaction is occurring and if chemical energy is being converted into electrical energy. Common electrical devices includes a galvanometer, which is an instrument shown here in the diagram which shows the magnitude and direction of the current, or another common device that we may use is a light bulb. There are a few key things, however, I would like you to be aware of when you're drawing your galvanic cell. Firstly, you'll need to consider what type of electrode you are using. Based on the redox equation, you will need to decide whether you will need a metal electrode, an inert electrode, and whether you may need a glass tube if you're dealing with a gaseous substance. If you are using an inert electrode, please ensure that you are specifying the material, so whether it's made from graphite or platinum. Sometimes questions may not tell you the composition of the electrolytes found in each half cell, so you may need to select appropriate electrolytes. Typically, the cations that we use in the metal solutions are made up of the metal ions, whereas the anions are often the spectator ions such as sulfates or nitrates. Similarly, the type of ions that we use inside of the salt bridge may not be specified by the question. In these instances, I would recommend that you use potassium nitrate or potassium chloride for the salt bridge. Furthermore, I would like to add that the anions that's used inside the salt bridge are often the same ones that's used inside of the electrolyte solution as well. Let's now go through a couple of examples at drawing labeled galvanic cells. In the first example, we are given the overall equation of the redox reaction. To begin, we should first identify the species undergoing oxidation and reduction and write the appropriate half equations. In this equation, I can see that the oxidation number has increased from 0 to a positive 2, suggesting that copper is undergoing oxidation. To write the half equation, we need to balance the charges by adding 2 electrons to the right hand side of the equation. Based on the mnemonic anox redcat, I know that oxidation takes place at the anode, which is the negatively charged electrode. On the other hand, chlorine gas is reduced, which occurs at the positively charged cathode. Because there are 2 chlorines, I'm going to first balance chlorines by adding a 2 in front of the chloride ion. To balance the charges, we then need to add 2 electrons to the left hand side of the equation. Now that we've got our half equations, we can now begin to draw our half cells. If we look at these half equations carefully, the half cell on the left involves a metal electrode placed in its metal solution, whereas the second half cell will require an inert electrode since chlorine is a gaseous reactant. Hence, a glass tube will also be required which pumps chlorine gas to the surface of the platinum electrode for the reduction reaction to take place. I would like to add that I didn't include any spectator ions in my electrolyte solution, but if you wanted to, you could also include either nitrates or sulfates. To complete the circuit, I'll now draw the external wires and salt bridge. We know that electrons flow from the anode to the cathode, so I'm going to draw arrows to show the movement of electrons. And lastly, we know that the cations of a salt bridge move towards the cathode and the anions move towards the anode. Even though it wasn't mentioned, you could be more specific with your drawing by specifying the actual composition of the salt bridge. So you could include the potassium ions over here, and you could also include the nitrate ions over here moving towards the anode. Let's look at another example. In the second example, it reads, a galvanic cell was set up by combining half cells containing zinc and magnesium electrodes dipped into the appropriate sulfate solutions. A conducting wire and the salt bridge completed the circuit. After 3 hours, the 2 electrodes were removed and weighed. The mass of the zinc electrode had increased, while the mass of the magnesium electrode had decreased. Draw the galvanic cell. Based on the first 2 statements, we should be able to visualize and draw the basic structure of our galvanic cell. For each half cell, the metal ions that I've used corresponds to the actual metal electrode that's present. The question also states that the mass of the zinc electrode had increased while the mass of the magnesium electrode had decreased. If you think about what happens at each half cell, we know that the mass of the cathode increases over time because metals are deposited on the electrode. Hence, this suggests that the zinc metal is the cathode while the magnesium metal is the anode. Based on this, we should be able to write the half equation for the reduction reaction of zinc, where zinc 2 ions gains 2 electrons to form zinc metal. In contrast, magnesium metal is oxidized and forms magnesium ions, which dissolves into the solution. Now that we've got the half equations, we can readily write the overall equation and identify the oxidants and reductants of this equation. The oxidants undergoes reduction, which is the zinc 2 ions in this case, and the reductant is the magnesium metal. All that's left is for us to show the movement of the electrons as well as the ions within the salt bridge. Again, remember, electrons always flow from the anode to the cathode. Similarly, if you wanted to provide more detail in this example, we can actually specify the actual ions used in the salt bridge. Since I can see that sulfates are used in the electrolyte solution, I could include potassium sulfate as my salt bridge electrolytes. What I would like you to do now is I would like you to now have a go at answering a question on your own. Please pause this video, and after you've completed your drawing, check to see whether you've got your answers correct. In this reaction, I know that lead is oxidized because the oxidation number had increased from 0 to a positive 2. Therefore, we need to add 2 electrons to the right hand side to balance the charges. To write the reduction half equation for chlorine gas, I will need to first balance chlorines by adding a 2 in front and then adding 2 electrons to the left hand side of the equation. Based on this, I should now be able to draw and label each of my half cells. We know that electrons flow from the anode to the cathode, so therefore it should move from the left to right on my drawing. Lastly, I'll need to draw the direction in which the cations and anions within the salt bridge move towards. Congratulations if you were able to make it this far in the video. By now, you should be fairly confident at drawing galvanic cells and are able to meet the following success criteria. This is the end of the video. Thank you for watching, and I'll see you guys again in the next one. Bye.